So our second speaker is Dosunmu-Ogunbi. She's a postdoctoral researcher at the University of Michigan, Ann Arbor. She very recently received her PhD in the robotics program at the University of Michigan, and she got her bachelor's degree in mechanical engineering with a minor in technology and management at the University of Illinois at Urbana-Champaign in 2017, and a master's degree in mechanical engineering at the University of Michigan, Ann Arbor in 2020. And she also has a master's degree in robotics at the University of Michigan, Ann Arbor in 2021. Her current research interests include controls with applications in bipedal locomotion. Specifically, she's developing robust stair climbing algorithms for underactuated bipedal robots, and she's recognized as a GEM Fellow and a Rackham Merit Fellow. Thank you very much. Go ahead, Wami.
Thank you for that introduction. I'm assuming you all can see my screen, correct? Great, thank you for that introduction. Hello, everyone. My name is Wami-Ogunbi, and this is my presentation titled Stepping into the Future, Unveiling a Novel Stair Climbing Controller. So I want to help create a robot-assisted world where robots of all types are working alongside humans from all walks of life. Think robot butlers and robot firefighters, robots doing the boring and dangerous task, while we humans get to do the fun and safe task. But in order for robots to be useful in this human-centric world that's built by bipeds and for bipedal beings, they need to be able to navigate through common human terrain, such as stairs. And so the objective of my work is to create a novel stair climbing control algorithm to allow for smooth navigation upstairs. That begs the question, though, can't bipedal robots already walk upstairs? Well, if we look into literature, we see that strides have certainly been made. So, for example, we're all probably familiar with Boston Dynamics and its Atlas robot that's able to navigate upstairs. However, I want to explore underactuated robots. Underactuated robots tend to be lighter and more agile. In this work right here, we have the authors use reinforcement learning in order to navigate up and down stairs using an underactuated robot. However, the algorithm treats the stairs as unseen perturbations, and thus quite a lot of torque is having to be exerted in order to make sure that the robot stays upright. You can imagine in delicate situations such as hospital settings, where this is probably not a comforting sight to see, a robot stomping up and down stairs in order to maintain balance. So I want to approach the stair climbing problem in a more gentler way. And then more recently, this work has come out where the authors were able to get this underactuated robot to navigate on constrained footholds, including on stairs. They approach the stair climbing problem in a different manner than I do in this presentation, which I will be discussing shortly. So the contributions of my work are as follows. I developed this new robot model that allows for smooth navigation for stair climbing gates. And I developed a novel control structure that includes the use of this underactuated motor, or sorry, this often neglected stance toe motor. So the rest of this presentation is outlined as follows. We already went through the motivation and background. Next, we will be discussing the system dynamics of the robot that we're of this presentation. We'll then talk about the controller design, as well as get into some results and end on future work. So let's meet Cassie. Cassie is the robot that I apply my controller on. Cassie is an underactuated robot, so it has 10 actuators total, 5 on each leg, and each leg is 7 degrees of freedom, where 2 of these degrees of freedom are passive. This right here represents the generalized coordinate vector of the Cassie robot, where the first 6 coordinates correspond to the floating base coordinates, and these 4 joints correspond to the passive joints. We classify systems like Cassie as hybrid systems. So what do I mean by that? So first, we have this continuous domain. This is when the swing leg, let's say our right leg, is up in the air. So, and right before it touches the ground, that ends the continuous domain. When it impacts the ground, that's when we enter the discrete domain for that leg. And of course, since we have 2 legs, we repeat this on the other side. So now we enter the continuous domain, this time for the left leg. It's in the air, and right before it touches the ground, we end that continuous domain. When it impacts the ground, that's when we enter the discrete domain for that leg. And of course, the cycle repeats for however many steps that you take. We're going to talk about the continuous domain, or look further into the continuous domain and see what the equations that govern this domain involve. So I used the floating base Euler-Lagrange approach to derive Cassie's robot equations, which we as roboticists are very familiar with this particular representation of the equations of motion. But even if you are familiar with this, I don't want you to be fooled by how quote unquote simple this equation looks. Because for robots as complicated as Cassie, these equations can be quite complicated. And I want to illustrate that to you. So let's look at the mass inertia matrix, which is this D matrix right here. And let's look at it for a simple robot, the 3-link walker, which is pictured in the upper right-hand corner of your screen. So if I were to draw out or write out the mass inertia matrix for this robot, it will look like this in Times New Roman 10-point font in Microsoft Word, which is not too bad. You could probably derive this by hand and it not be too bad. So now let's get a little bit more complicated. Let's look at the 5-link walker. So it's still a planar robot, but now it's 7 degrees of freedom. What does the mass inertia matrix look like for this robot? It looks like this. And already you can see things are getting a lot more complicated because now we're using distributed mass. So now we're up to 5 pages, which is quite a lot, way too much to derive by hand. And now let's see for the Cassie robot. Can it be that bad? Cassie doesn't think so, but I say it is that bad. In fact, it takes up thousands of pages in order to just write out Cassie's mass inertia matrix. So all that to say that Cassie is a extremely complicated robot. And again, do not be fooled by how simple these equations of motions look like for this continuous domain. So how do I control this extremely complicated robot, and how do I get it to climb upstairs? Let's take a look at my algorithm. So starting with my control design philosophy, we need to regulate 20 degrees of freedom. How do we do that? So 9 of them are actually already taken care of due to the holonomic constraints during continuous phase. Specifically, there's 4 coming from Cassie springs, and there's 5 coming from the stance foot. I'm then going to choose to use 9 of Cassie's 10 actuators to control 9 degrees of freedom via passivity-based control. And then I'll use that 10th actuator, which is the stance toe actuator, to control the sagittal plane center of mass dynamics. And here I want to point out, this is one of the innovations of this work, because previous methods would use foot placement to control this particular plane of motion, but I'm using the stance toe actuator. And the reason for this is because think of the geometry of stairs. There's typically limited space for you to move in that sagittal plane. So foot placement in that particular plane of motion does not make sense. Hence why I use the stance toe actuator. And now for that final degree of freedom, I'll use lateral foot placement to control the frontal plane center of mass dynamics. And now you might be thinking, wait, Wami, why are you using foot placement in this plane of motion, whereas you didn't or couldn't use it in the sagittal plane? Well, again, I would invite you to think about the geometry of stairs. Stairs are typically pretty wide, so using foot placement in that particular plane of motion still makes complete sense. So that's my control design philosophy. Let's look at the control structure here. So the first thing I needed to do was generate the nominal trajectories for to control this robot. And then I also needed to have some sort of a robot model, a new and improved model that's better than the old model. And then I was able to develop this virtual constraint-based control using the passivity-based control method, which I hinted at in that last slide. And then I want to point out here that the desired trajectories that we follow in the virtual constraint-based control, we use the trajectories that we generated in the first step. And additionally, the new model that I developed is also being incorporated in this particular step right here. Then we have this intelligent ankle torque computation plus lateral foot placement strategy. And again, I use the nominal trajectories from that first step in this particular um, uh, part of the controller, as well as that new robot model is also being incorporated here in this particular part of the controller. And all of this taken together results in stair climbing. We're not going to have time to go through each of these particular segments, but I'm happy, of course, to answer questions about these if you are curious. So for now, we'll just look at just this new and improved robot model that I developed. So, but before we can talk about the new and improved robot model, we need to know where we came from. What was the old model? Well, we used to use what's called the linear inverted pendulum model, which, if you're not familiar with, is basically a simplified representation of the dynamics of an inverted pendulum. So for bipedal robot applications, we would use the LIP model by basically assuming a point mass on massless legs. So direct your attention to the image of the CATSI robot that I have in the bottom left-hand corner of the screen. If I were to write this as using the LIP model to model this robot, it would look exactly like this. Now, assumptions or applications of the LIP model would typically assume constant center of mass height, and it would use center of mass velocity to quantify what we call balance. And what we'll see is that these assumptions are not good for stair climbing applications. So now we upgrade that LIP model and now use the ALIP model, the Angular Momentum Linear Inverted Pendulum model. And as the name implies, the ALIP model is basically another derivation from the LIP model, but instead of using center of mass velocity as the key variable, we use angular momentum instead. Why this change? Well, let me show you how center of mass velocity evolves over time for the LIP model. So it looks like this on this graph. And then if we were to compare this to the full order model of CASI, the center of mass velocity would look like this. And as you can see here, there's discontinuities in that on the CASI model that you don't see in the LIP model, which is not good. The reason why we use reduced order models like the LIP model is so that it can be a fair representation of the full order model of the robot that we're trying to represent. But as you can see that these two graphs look completely different, that the LIP model is not acting as a fair representation for the CASI model. So now let's look at how angular momentum evolves about the contact point. And so for the LIP model, it looks like this. And now for the full order model of CASI, it looks like this. And now you don't see these discontinuities that appeared in on the previous graph. And in fact, we see now that the ALIP model is basically, it functioned as a better representation for the full order model of CASI. So with the ALIP model, I actually take it one step further in my research. So previous applications of the ALIP model, they would define the center of mass states like this, and then find the full order center of mass dynamics like this, where the LYC term is actually proven to be negligible for CASI-like robots. And then here, this is where things get interesting. They would make a constant center of mass height assumption so that this term, this Z dot C term, would go to 0. For my new variation of the ALIP model that I introduced in this work, I reparameterized the ALIP model once again, and now introduce these two new variables, theta C and RC, which is the center of mass angle, as well as pendulum length. And I now thus define my center of mass states like this, where you can already see that theta C variable already showing up. And now my full order center of mass dynamics are defined like this, where we know for CASI-like robots, this LYC term is still negligible, that hasn't changed. But now, instead of a constant center of mass height assumption, I make a small angle approximation and say that sine theta C, or theta C, is sufficiently small enough that sine theta C is approximately equal to theta C. And to really kind of just like drive this point home, this RC term, this pendulum length term, which basically acts as a proxy variable to center of mass height, that is time varying, unlike in that previous version of the ALIP model. So that's the new and improved robot model that I introduced in this work. And again, we don't have time to go through each of these other areas of this controller that I implement. but happy to answer questions about those later on if you have them. So let's look at my results. So first starting with sim mechanics simulation. So a quick note about this environment. We do incorporate compliant ground. We factor in Cassie springs, as well as we're implementing the full controller as we would on the actual hardware of the robots. State estimation is being used exactly as we would use on the hardware, and all the computations are happening in real time, which means that they have this 2 kilohertz execution time, which is extremely fast. And so all that to say, this is a very rigorous simulation environment, which is why we love to use it in my lab, because controllers that work in sim mechanics tend to also work on hardware. So when I apply this controller in this environment, we see that Cassie is able to navigate all the way up the stairs, specifically when that ankle torque is being engaged. And just to test it out, we saw what would happen if we turned off ankle torque, and we see that that Cassie is only able to make it a couple of stairs or steps before it falls on its back. And something that's really interesting here is that if we look at the values of the ankle torque, we see that the magnitude is actually pretty small. And yet this little bit of ankle torque is the difference between whether Cassie can make it all the way upstairs or fall back on its back. Now we want to try hardware, and Cassie being a very old robot that is no longer under warranty, we want to be very careful and intentional on how we test our controller. So we take incremental steps before, I guess, going all the way, testing really dangerous experiments. So the first thing that we do here is we have Cassie walking on a treadmill that is going at 0.9 meters per second. And this treadmill is slowly inclining from 0 degrees all the way up to its maximum incline of 20 degrees and then back down to 0 degrees. And we're not going to have time to play this entire video, but the QR code to see this video is on the top right-hand corner of the screen. It will stay there for the next few slides. So you're welcome to access all my experiments using that QR code right there. But what I want to highlight for this experiment is that we only use 3 nominal trajectories when implementing this experiment. And this tells us that we don't need to have a nominal trajectory for every single specific circumstance that we're trying to test under. One nominal trajectory is good enough to be applied on a wide range of applications. So this just shows the robustness of the controller. In this experiment, we have Cassie walking from stationary flat ground to a treadmill that's inclined at 20 degrees and is also moving. So again, I want you to think about like you trying to walk on a treadmill, walk from flat ground to a treadmill that's inclined and moving. That's difficult for even us humans to do. So you can imagine how difficult it is for a robot to accomplish. So this just shows, again, the robustness of the controller. And when we get Cassie to get on that treadmill, we have the treadmill start to increase its speed to 1.5 meters per second. And you can see that the controller is still functioning just fine. So in addition to stairs, there's also moving walkways that we encounter in real life. You might see these in like airports or some fancy malls. The speeds of these moving walkways would be typically from about 0.5 meters per second to about 0.8 meters per second. So we get Cassie to try to walk on this moving walkway that's moving at 0.8 meters per second, which is that upper speed. And something I want to point out is that the gantry, which is basically this thing right here that would catch Cassie if it were to fall, it's acting as a very large disturbance because the gantry is not designed to move as far back as we needed Cassie to start in this experiment. So while Cassie is trying to walk, this gantry is kind of tugging at it, and yet the controller is robust enough such that it's able to overcome that large disturbance and complete this experiment. We have Cassie also move on a walkway that's at 1.2 meters per second, which is faster than what you would see in real life. And in this experiment, you're going to see that Cassie's about to stumble in a couple of seconds right there. So yeah, Cassie stumbles And again, this is due to that gantry that's acting as this very large disturbance. And yet the controller not only is able to recover from that stumble, but it's also still able to walk across this very fast moving walkway, faster than you would see in real life, and complete the experiment. So in this presentation, I talked about this new novel stair climb controller that I developed. We specifically covered the new and improved robot model, the new ALIP model. There's other parts of this controller that we didn't get to today, but I'm happy to talk about in the Q&A. And we're able to apply this controller on a full order model of Cassie in both a sim-mechanic simulation environment and on hardware. The next steps would be to apply this controller on hardware on stairs, and as well as to explore downstairs walking. And with that, I would like to thank you for your kind attention. I have QR codes linked to the videos, as well as to my website on the screen. And with that, I would like to take your questions. Thank you.